Hello viewers. In this chapter, we will discuss two crucial physical quantities related to rotational dynamics, torque and angular momentum. Before going to the rotational dynamics, let us first recapitulate the motion of an object with examples. In the first example, let us consider a rectangular block is sliding down over an inclined plane. In this example, all the particles of the rectangular block are moving together. That is, they have the same velocity at any instant of time. In this translational motion, all the particles cover equal distances and the line joining any 2 points at the initial position and at the final position shall become parallel to each other. In the next example, instead of placing a rectangular block, if we put a cylinder, instead of simple translational motion, we will observe the object rolling down the inclined plane. In rolling, the velocity of all the particles of the moving object doesn't remain the same. There is also no fixed pattern for the lines joining any 2 points before and after the movement's completion. On closer observation, we can find an axis that does not undergo any rotation but moves parallel to the inclined plane and behave as if a translation motion just took place. Therefore, rolling motion is a combination of translational motion plus rotational motion. In the next illustration, we will represent rotational motion. In the rotation of a rigid body about a fixed axis, every particle of the body moves in a circle, which lies in a plane perpendicular to the axis and has its center on the axis. The main characteristics of rotational motion is that in rotational motion, the particles subtend equal angles irrespective of their distances from the axis of rotation. Moving to the main physical quantities related to rotational motion. The first important physical quantity is the angular displacement. It is the angle which a particle in rotational motion creates at the axis of rotation. The next one is angular velocity, which is defined as the rate of change of angular displacement with respect to time. Similar to the acceleration in linear motion, here in rotational motion, we have angular acceleration. It is defined as the rate of change of angular velocity with respect to time. Like the equations of motion in linear motion, we also have equation of motion for rotational motions. These equations can be derived easily starting from the definition of basic physical quantities associated with rotational motion. We can obtain the relation between the initial and final angular velocity from the definition of angular acceleration. Omega equal to omega naught plus alpha times t. Here, omega stands for the angular velocity at a time t and omega naught stands for angular velocity at the initial time, that is t equal to 0. We can obtain the relation between the initial and final angular displacement from the definition of angular velocity. Theta equal to omega naught times t plus half of alpha times t square. Here we have considered initial angular displacement of the particle is 0, that is theta naught equal to 0. Starting from the definition of angular acceleration, we can relate the change in angular velocity with angular displacement and time. It looks like omega square minus omega naught square equal to twice of alpha theta. Now let us move to our main point of focus, that is torque. Torque is the analog of force in the rotational motion. It is also described as the turning effect of force. Let us elaborate on this concept with the example of a wrench and a bolt system. Our experience in opening a similarly tightened bolt depends on at what distance we are applying the force, or what is the magnitude of the force, or at what angle we are applying the force to rotate the bolt. If the arm length is big and we are able to align our force exactly perpendicular to the lever arm, then it becomes easiest to rotate the bolt. Based on this experience, torque is defined as an effect produced by a force about the axis of rotation which is equal to the product of the magnitude of the force and the perpendicular distance of the line of action of the force from the axis of rotation. Mathematically, it is expressed as tau equal to r cross f. Its magnitude can be represented by tau equal to Rf sin phi. Here, phi represents the angle between R and F. So, this expression explains why we feel it is easy to open a bolt when we apply force at a greater distance from the axis of rotation, or when we apply the force exactly perpendicular to the wrench lever arm. Obviously, if we apply more force, we can open the bolt easily. However, if the direction of the applied force is directed towards the axis of rotation, then we won't be able to rotate the bolt at all, no matter what amount of force we are applying. In this case, phi equal to 0 makes the torque value to be 0. Torque is a vector and its direction is obtained applying right hand thumb rule. So far, we have got an intuitive approach to quantify torque. We can even obtain the expression for torque directly by application of vector algebra, which we are going to discuss next. Let us consider we are applying a force F on a particle at position R and it produces a turning effect about an axis O. We can consider a coordinate system and the whole observation is depicted as top view. Here, the starting point is the quantification of work done in this process. If we correlate work done in the linear and rotational system, we can get the expressions for torque out of this process. Remember, the definition of torque is based on the consideration where torque in rotational motion plays a similar role to force in linear motion. If the rotational displacement due to the application of force F is very small, then we can assume ds as a straight line and obtain expression for work done by the application of force. With certain mathematical steps, we can represent the same work done in terms of some quantity times the angular displacement as W equal to x Fy minus y Fx times d theta. This says torques must be x Fy minus y Fx. It suggests the expression for torque is going to be tau equal to R cross F. From the above representation of work done in terms of torque and angular displacement, we can also evaluate power associated with torque as P equal to tau times omega, where omega stands for angular velocity. Another important physical quantity associated with rotational dynamics is angular momentum. When an object moves about some axis, there is momentum associated with rotational motion called angular momentum. Angular momentum is the rotational analog of linear momentum. Like the moment of force, that is torque, angular momentum is also a vector product. It is often referred as moment of linear momentum. From this term, one can guess how angular momentum is defined. Consider a particle of mass m and linear momentum p at a position r relative to origin O. The angular momentum L of the particle with respect to the origin O is defined as L equal to r cross p. The magnitude of angular momentum is L equal to rp sin phi. Like torque, angular momentum is also a vector quantity and its direction is obtained applying right hand thumb rule. Taking a derivative of definition equation for angular momentum, we can relate angular momentum and torque as tau equal to dl d theta. The above equation suggests that if no external torque is applied on the system, then its angular momentum should be constant. This is often named as law of conservation of angular momentum. We can also have a geometrical interpretation of angular momentum. Suppose the position of a particle moving with velocity v is represented by the position vector r. After some time delta t, the position of the particle is changed and represented by r plus delta r. Geometrically, using vector algebra, we can show the angular momentum of the particle around the axis is equal to twice m times areal velocity of the position vector. This geometrical interpretation can be used to explain Kepler's law, which we shall discuss while discussing gravitation. To summarize, in this chapter, we have discussed types of motion, torque, angular momentum with detailed representation and physical significance.